Hello, everybody, and welcome to Tuesday, March 24th. Of course, here we are stuck in the land of the plague. The whole world is waiting to see what's coming down with the coronavirus. And we are SciTechNature, although I think for a few moments we should be SciTechNature and perhaps a little humor as well. So let's start with the such a lovely message to the world. Almost makes me cry. And now perhaps a little bit of something to make you laugh. We could use that at the moment.
So, Chuck, how's the job search going, huh?
I got something, Sam, but I'm not too excited about it. I'm a janitor at a biology lab where they do DNA experiments, making mutant viruses and stuff.
Well, that sounds like a pretty good job.
I don't know. It makes me nervous, all that weird stuff floating around.
Oh, don't worry about it. I'm sure it's safe.
Oh, yeah, absolutely. They keep all the right precautions. Yeah, no problem.
I guess you're right. Must be getting a little paranoid, huh? I feel better already. See you later.
Yeah, take care, Chuck.
Whoa, whoa, whoa.
These two wonderful uplifting sequences were brought to us by Terra. Thank you, Terra. That was really great. I've always had a bias towards the macrocosm, the large things, the stars, the galaxies, the size of the universe, and my knowledge of the microcosm has leaves much to be desired. So I'm going to drag you on my subjective trip into the microcosm, which seems appropriate at the moment, seeing that we're dealing a lot with the theme of viruses. And I thought I would start off with a little history, and then we'll see where we go from there.
While the telescope has made it possible for us to view the cosmos, the microscope has allowed us to see the smallest components of all living things. Magnifying glasses are mentioned in the writings of Roman philosophers during the 1st century AD. But it wasn't until the 17th century that Galileo, the father of modern physics and astronomy, formulated the principle of lenses and focusing. Robert Hooke built the first usable British compound microscope in 1665. It was a light microscope with two converging lens systems, the objective and the eyepiece. Hooke observed that tissues were constructed of many tiny individual building blocks. In 1665, he had discovered and named the cell. Hooke was actually viewing cork, dead plant cells. The first person to witness a live cell under a microscope was Anton van Leeuwenhoek. Around 1670, Van Leeuwenhoek developed a method of grinding very thin glass lenses, just a millimeter in diameter, and yet they could magnify by several hundred times. These single-lens microscopes were far superior to the early compound instruments. Mounted in a brass plate, these lenses could use transmitted light to image objects in a drop of water on the end of a metal pin. A screw was used to move the pin and focus the specimen. Van Leeuwenhoek was the first person to see and describe bacteria and yeast cells, sperm and blood cells, and witness the circulation of blood through capillaries. Light microscopes are still used today, but in 1931, German scientists Max Noll and Ernst Ruska invented the electron microscope. Instead of light, this microscope employs a focused beam of electrons to image the specimen, and is capable of far greater magnification and resolution. The electron microscope can magnify up to 1 million times, making it possible to view objects as small as the diameter of an atom. These powerful microscopes have one major drawback. Living specimens are destroyed by the high radiation of the electron beam. And so scientists must continue to rely on traditional light microscopes to examine living cells.
So seeing that history really gave me a want to see what these creatures were like in their sort of average everyday lives. And I found this really interesting video, which I'm going to play you now.
Despite huge differences in morphology and biological structures, all living organisms do the same three basic things. They get food, digest it, and excrete waste materials. Living organisms require energy to live. Some produce their own food, usually through photosynthesis. We call these autotrophs. But many organisms cannot make their own food. We call these heterotrophs, and they eat. Among heterotrophic single-celled eukaryotes, food is taken into the cell in various methods, but once it's there, it's wrapped by a membrane and forms something called a food vacuole. Then the cell flushes digestive enzymes inside the food vacuole to start the digestion. Nutrients are taken into the cytoplasm, and the waste material left in the vacuole then basically fuses with the outer membrane of the cell, and what's left in the vacuole is discharged into the environment. In some cases, like inside this beautiful single-celled Nacella ornata, which feeds on filamentous cyanobacteria, content of the food vacuole reacts with the digestive enzymes and changes color. But that process takes time. Because each vacuole formed at a different time, they are in different stages of digestion, which gives this cell its colorful polka dots. But how do these heterotrophic organisms get their food? Well, in spite of a remarkable amount of diversity, a lot of microorganisms use one of the same 3 strategies for getting their food. Some of this will be familiar to the macro world, some of it will not. One of the less familiar is filter feeding, which allows larger organisms to consume suspended food particles or much smaller organisms. There are filter feeders in the macro world. Baleen whales come to mind. But while a whale must swim through giant clouds of small organisms in the microcosmos, your food can come to you. Some filter feeders use hair-like structures called cilia to create a vortex that brings other microorganisms or food particles to the cell mouth. These cilia are specialized for this task, and their beating creates a current that expediently and beautifully directs every nearby thing into the waiting mouth of the microorganism. The cilia are often too small for us to see, but you can see their effects. Take a look at these paramecia. They're consuming tiny bacteria, and you can see their cilia causing small organisms to tumble across them. You can also see all of their food vacuoles on the inside, and if you look very carefully, you can see a new food vacuole forming and getting filled up with those tiny bacterial cells. Some of the best and most obvious filter feeders are rotifers, microanimals that use cilia to create swirling vortices around their mouth parts. You can see how successful this feeding strategy is by its belly full of algae cells. Every time its mouth fills with more algae, it contracts to swallow the food. Now observe these single-celled organisms called stentors. They are much bigger than most other microorganisms. You can actually see them with the naked eye. And they also use filter feeding to push all of their algal food into their cell mouths. Our second feeding mechanism, maybe the most familiar and the most exciting, is called raptorial feeding. Raptorial feeders selectively capture prey and hunt other organisms. In this video, you can see Dileptus hunting. It paralyzes one organism with a touch of its trunk-like proboscis, and then it pulls that organism into itself in a process called phagocytosis. Many of these microorganisms are armed with something called toxicysts. These are little harpoon-like structures filled with toxins, and they're located on a particular part of the cell which the microorganism uses for hunting. These tiny harpoons are then fired when they come in contact with prey organisms, which then become immobilized. This is Bursaria. It's a single-celled organism with a huge mouth, and things have not gone well for the paramecium that is now inside it. The paramecium dies immediately because of the toxicists on the inside of the Bursaria, so at least it was quick. Now get ready for some truly gorgeous footage of a microanimal's day going south. First, Paradileptus immobilizes the rotifer with fired toxicists, and the animal is swallowed by the single-celled organism as it swims away. This is Frontonia, which is a close relative of Paramecia, but it lacks the filter-feeding habits of its relatives and feeds predaciously on large diatoms and filamentous cyanobacteria, such as Oscillatoria here. Though in this case, it turns out this Frontonia bit off a little more than he could chew. Another raptorial feeding style is called histophagy. Histophagous organisms, such as these single-celled coleps, attack injured but live animals or other single-celled organisms, sucking off hunks of tissue rather than consuming whole organisms. When they attack an animal, they enter wounds and ingest tissue, often attacking in groups because their chemical sensing abilities attract many of them from a distance, like microscopic vultures. When a number of them gather in one place, it's hard to avoid another macro-world analog, piranhas, devouring everything soft in no time at all. There's a huge variety of raptorial feeding. This is just the beginning, but we wanted to show you one more before we move on. This is Vampirella, an amoeba with a suitable name. It specializes in feeding on filamentous algae. First, it bores a hole through the algal cell wall, and then slurps out the gooey, nutritious cytoplasm. Our final feeding mechanism, for today at least, is diffusion feeding, in which the predator just sits in the same place, relying on the prey to accidentally make contact. This is a heliozoa. It's a single-celled amoeboid, and because of its resemblance to the sun due to the rays coming out of its cell, it's sometimes called the sun animalcule. The rays are called axopodia. These are sometimes used in locomotion, and in this case, for hunting prey. Axopodia are cytoplasmic extensions, meaning they're a part of the cell membrane, even though they look like they're sticking out of it. Each one has a central supporting rod of microtubules that gives it this rigid structure. The axopodia are coated in organelles that discharge toxins when touched, which impair or even paralyze heliozoa's prey. After the organism is captured, those microtubules are drawn back into the cell, thus retracting the axopodia and allowing the cell to swallow the unlucky organism. Or prey is just engulfed by extrusions from the cell called pseudopodia. In this video, a rotifer has been captured by a heliozoa and is slowly getting eaten by it. Now, this is something that happens fairly frequently, but we did capture something unusual here. While it was stuck to heliozoa's axopodia, this rotifer actually lays its egg, but neither egg nor the rotifer is going to escape this. Surprisingly heartbreaking. This is a suctorian. It's a ciliate, just like Paramecium and Stentor. These organisms have hair-like cilia during the early stage of their life, but as adults, they develop bundles of tentacles. Just like in Heliozoa, these tentacles are supported by an internal cylinder of microtubules. The tip of the tentacles have extrusomes. These are special structures that attach to and immobilize any other ciliates that touch them. The tentacles eventually penetrate the cell membrane of the prey, and then the contents of the prey is sucked out through the tentacle. In this clip, a suctorian has caught 4 individual vorticella with its tentacles and is slowly sucking their cytoplasm. It looks a little like the vorticella have the suctorian surrounded, but in fact, they are powerless to escape it. It's a dangerous world out there. The complex chemicals created by organisms to sustain their life necessarily are useful to other organisms as building blocks and as fuel. And so predation evolved. It's beautiful, it's constant, and it's brutal. Thank you for watching.
And if you want to subscribe, you can see the subscribe button right up there. And I've watched several of these, and it's just fascinating watching the creatures that you can't see having their lunch and dinner. Now I'd like to switch to the larger cosmos. So we're going to look at something slightly more expansive, the universe. And if you can see here, here's where we are now. This is a timeline from the moment of the Big Bang to the present day. Now, one of the things that's becoming very interesting is as you go back in time to this very, very early stage, they're starting to look whether they're presently using the Hubble telescope to do this. We're very much looking forward to the Webb telescope, which is 20 times more powerful than the Hubble telescope, to look deeper towards this, what they call the event horizon. But what they're seeing with the Hubble telescope are galaxies and stars in an area that should be so early that all you should be able to see is primordial gas or subatomic particles. So, not to put too fine a point on it, the cosmic timeline has some serious problems.
The cosmic timeline is not difficult to understand. Before the formation of galaxies and stars was the formation of atoms, before that subatomic particles, cooling and expanding from the initial moment of time, the Big Bang. Problem is, the cosmic timeline is wrong. The cosmic timeline problem was addressed in part by Dr. Fulvio Melia in our full plasma cosmology film. The problem was that if the universe began 13.8 billion years ago, as is said to have occurred, then we see some things in the early cosmos that present some challenges to that paradigm. The first is the formation of supermassive galaxies, which formed so quickly that at that point in the cosmos, the first stars are supposed to still be coming together and igniting. Yet they see numerous cosmic monsters with the maturity of ages in deep space. He also mentioned the quasars, the powerful cosmic jets. With such power, they must have incredible masses, which is also a problem at an age in the universe when stars a billionth of its size are supposed to still be forming. Now, in the wake of that film, we've seen the discovery of enormous early protoclusters and galaxy groups, again, at ages that challenge what was supposed to be going on way back then. But beyond the supermassive galaxies, the quasars, the galaxy clusters, and protoclusters, let's hear the knockout punch from our October 2019 short summary. Perhaps the most damning evidence comes from individual stars. They say that the earliest that stars could have formed was 200 million years after the Big Bang, but there are at least 2 stars we know of, not just in our own galaxy, but within 1,000 light years, that are as old as the Big Bang or older. Methuselah's star is thought to be 14.5 billion years old, maybe older, and is only 200 light years away. The galaxy is 100,000 light years across, so what are the chances it's the only one that exists? The only one that exists in our galaxy. Now to summarize, the universe age is wrong. It's one thing to look deep into time and see strange things, but when you have a star 14.5 billion years old, traipsing around only 200 light years away, you have a major problem in the cosmic timeline. There are likely dozens of Methuselahs just in our galaxy alone, and as fun to think about as that is, the implications for the universe are virtually unexplored, ignored as a problem by cosmologists. Does this seem simple to understand? Yes, it is, but finding the answer might be a bit more difficult.
This is just one of the questions that have emerged in modern cosmology. The other one that seems to be a continual sticking point is the search for dark matter. The dark matter search has been gone for years now, and paper after paper is showing no sign of dark matter.
Folks, they had high hopes for the dark matter search at Gleam. Careful observers will remember this no-show is the third one looking at the dwarf galaxies of the Milky Way in just the last few months. But then there are the dark matter searches the entire world of physics waits for. They have hundreds of the world's top scientists carefully analyzing every inch of the experiment and data and potential interpretations. The Ice Cube and Antares missions teamed up to form a supergroup, one containing researchers from nearly every top university in Europe, a number of others across the remainder of the world, and over a dozen U.S. institutions including MIT, Berkeley, both Cal and the National Lawrence Livermore Lab, Yale University as well, and of course, Oxford, the perennial global top 5 university out of the UK. All in all, that is a lot of funding and time and brain power and effort to come out and say you found absolutely nothing, just as long as they know they tried and we're proud of them.
You may remember earlier this year that I gave a presentation on the dangers of groupthink, that a group of people come together with what seems like a really good idea, and even if it turns out to not be a good idea, it's too late because there's so much investment locked into it, so many ideas and leaders who are running this particular group, that anything that comes from the outside and says, well, it might not be true, just gets brushed aside. This phenomenon usually happens more when there is less data and more interpretation. And I addressed this problem in this presentation I did on groupthink and heresy, and you might want to consider that in the light of the next things that I'm going to show you. I did a discussion about the black hole, the highly sensationalized, publicized, round the world orange donut, which was claimed to be a black hole, to which a lot of the plasma physicists just rose in fury and frustration over, because it just seemed to them to be absolutely ridiculous that you could consider this a black hole. It looks a lot more like a toroid, which is more in line with what one would expect from a plasma configuration than it ever would a black hole. Anyway, I suppose because the donut was so embarrassing, they decided to revamp the data, and you can see here there's a new article just came out on March 18th, where they redo the data so that they can see it in a different way. And again, the plasma physicists have some thoughts on that.
Let's go ahead and begin with the imagination. Folks, the background on this is 2 parts. First, there is the famous black hole image they released last year. And second is the debunking of that image by Dr. Robitaille in numerous papers, and which he made a few special videos about on his channel, Sky Scholar. Here, the scientists doubled down on their methodology, suggesting improvements can be made to the detail. Now, while the animation is beautiful, and I'm sure their math is too, every single aspect of the model is guessed. Their paper is up as well, and boy, it would be great if Dr. Robitaille could demonstrate where all these Harvard, Princeton, and NASA scientists went so wrong.
Perhaps that's enough about cosmology and heresies for a little while. I'll come back to it, you can be sure of it. But for today, I'd like to move over to Indonesia. I recall seeing a National Geographic from the 1980s, early 90s, which basically said, what amazing how fast the fauna and flora could come back to an island so devastated as Krakatoa. Krakatoa, as you may remember, I don't know how old you are, but you may have learnt that Krakatoa blew up in mid-1800s and wreaked terrible havoc throughout Indonesia and the tsunamis that killed over 30,000 people. This National Geographic was describing a placid island that was getting back to normal. And, I really hadn't paid much attention to Krakatoa since then. So, I didn't know. So I went and looked it up, and oh boy, was I surprised. I've placed the video down in the links here. I'll play you a little bit of the last part of the videos that have been taken recently of this devilish volcano. as I watched the end of that volcanic eruption, I thought, well, there you are then. It's left everything a total lunar landscape. All the flora and fauna is absolutely devastated, and it's settling down now to a nice and peaceful rest. And then it blows up again. Nature is just astonishing. And last but not least, I have a link from Rob Lerner, which is the Learning from China, 7 high-tech strategies for pandemic containment. It will be down in the links down here. I've read some of it. It's fascinating reading. I hope you enjoy it. And I think that's it for today. And I'll look forward to doing another presentation next week. If you have any questions or any suggestions, please let me know. Again, you can leave a message, I believe, right down here. And I would like to know what you think. So everybody, be safe, and I'll see you next week. Goodbye.